All right, let's get started. So thanks for everyone who was able to join us with the webinar, either via Zoom or also live through YouTube. This is our first GPU Accelerated Data Science webinar of the year, so we're really excited. Tom Drabas is going to be joining us and is going to basically show very quickly how you can get started with Blazing SQL and RAPIDS and why this technology stack is such an effective stack for very quickly and easily doing large-scale data processing, but also, some smaller-scale data processing, but just wildly faster. I'm going to give a quick overview over the ecosystem before we get started, and then Tom will take over with his demos, where he'll do a hands-on demo that everyone can follow along with, and then also scale that demo up to a multi-GPU demo, so you can see how it is that you can scale up these problems to bigger and bigger problem sets. So let's just get started. So, for anyone who's not familiar, Blazing SQL is a GPU accelerated SQL engine. It basically does all the computational components of a SQL query processing on the GPU itself, which enables us to gain a lot of benefits in terms of performance when it comes to running queries. So the simplest and easiest way to think about Blazing SQL is it's an engine that does SQL on data frames. So for anyone who's familiar with pandas and pandas data frames, this code here should look very similar, very typical for you, where you can read in a CSV file into one of these data frames. Instead of pandas, we're using a library called cuDF, which is part of this RAPIDS ecosystem. And this is now a CSV file as a data frame inside GPU memory. And so if we want to create a table off of it with Blazing SQL, we have this concept of a Blazing context where we can create the table, we give it a name, we pass the actual data frame, and now we can run queries on in-GPU memory objects. And there's also ways where instead of, passing an actual data frame, you could actually pass the CSV file path. You can pass a directory that has, many files. Maybe they're Apache Parquet files, JSON, CSV, Apache Orc, etc. And you can run SQL queries directly off of that. Conversely, you also have the cuDF data frame where you can interact with pandas-like APIs. On that same data frame. So this whole technology set is part of a greater ecosystem. That greater ecosystem is called RAPIDS. RAPIDS enables you to do end-to-end data science analytics on GPUs. Blazing SQL is the SQL engine of RAPIDS, but there's also cuDF, as we mentioned before, which is effectively pandas or the data frame on RAPIDS. There's cuML, which is effectively scikit-learn on this cuDF data frame, and is also running in GPUs. cuGraph is graph analytics, and so on and so forth. And where Dask comes in, for anyone not familiar with Dask is how we scale up Blazing SQL in the RAPIDS ecosystem from one node or one GPU to, n nodes. We've gone as large as 700 nodes, actually. So that's 700 GPUs that are intercommunicating with each other and working together. We do that on, supercomputer-like systems, so or not even supercomputer-like, supercomputer systems. So very rarely do people have access to 700 GPUs, but that's, the largest scale Blazing SQL and Dask cluster that we've run in the past. So yeah, real fast, just, like I was mentioning, there's the SQL engine, there's cuDF, which is the data frame, there's machine learning, graph analytics. It plugs in with a variety of other technologies. And what Tom's basically going to go over is how is these first two libraries, Blazing SQL and cuDF, and how you can get started with the ecosystem. So with that, Tom, I think it's your turn to start sharing.
Roger that. Thanks, Rodrigo. Welcome, everyone. Thanks for joining us on the first webinar of the year. Let me start sharing my screen, and I think we can get this off, hopefully to a good start. So first things first, as Rod mentioned, if you are not familiar with the with our platform, just right now, if you wouldn't mind going to app.blazingsql.com and use your Google credentials to just log in to the service. And that will start a, a free server. So everybody gets a chunk of a T4 that that powers our free offering. And without this, we are good to go. Now, couple of things for those of you who might not be like entirely familiar with the with the service. We are running a Jupyter lab, so you can look, and everything is organized into folders. So this is our main folder where we're going to be working off of. If you want to pick into how much data and how much memory you are using, you can navigate to this icon here, System Dashboards. And over here, you can grab GPU resources and drag them to the side. This is rescalable, so I can move it around and dock it pretty much anywhere on my screen. So that way, I can monitor what's happening. Is my query running or anything else. Now, for those of you that have used, haven't used our service before, the welcome to Blazing SQL notebooks will have a folder called Webinars, and inside you should have Air Transport folder with a Getting Started notebook inside. If you do not, have that webinar, have that folder, we are going to actually do that right now and clone it. So first of all, if you go to github.com and go to, I'm going to paste that in the chat window here. If you go to navigate to that that GitHub repository, just do a git code HTTPS and copy that link. And I am already here. So most likely you won't be able to just pull the repository itself. So we're going to rm-rf welcome to Blazing SQL notebooks. We're going to delete that and then just do a git clone of that repository here. So we're going to navigate to the root folder. There we go. Everything is getting cloned down. OK, so now if you refresh, you should have the newest version of Welcome to Blazing SQL notebooks. And if you click on webinar, you should see Air Transport notebook over there. If you do not, raise your hand, and I can slow it down a little bit. But I'm going to assume from now on that we are seeing the Getting Started notebook over here. So I'm going to minimize that, and then we can get on. So as Rod said, Blazing SQL is a SQL engine for the RAPIDS ecosystem. So we are able to express ourselves not only in terms of pandas API, just like QDF that supports pandas API, but if you are more familiar with SQL, you can express yourself in SQL using Blazing SQL. And for me, this is a perfect extension of the ecosystem itself. Why? Because certain things are easier to do in SQL versus pandas, and then certain things are easier to do in pandas API rather than in SQL. And having this collaboration or interpretation from both sides helps you to utilize the benefits of both sides. Blazing SQL, whenever you run a query, SQL query, it returns a QDF. Unless you run the Blazing SQL on top of the Dask cluster, then we get back a Dask QDF. And as Rodrigo mentioned, Dask is our way of scaling up beyond a single machine with a single GPU to multiple machines or multiple GPUs within a single machine, or multiple machines with multiple GPUs whatsoever. So first of all, we're going to start with all the imports that we are going to need today. So first, we import SQL. OK, that is restarting. So I'm going to restart that again, just for a good measure. And let's start again. So I am importing QDF. QDF is our RAPIDS ecosystem data frame. Blazing SQL is the Blazing SQL import. S3FS we are going to use to query the data that lives on S3. What Rodrigo also mentioned, that you can read different files, on different in different formats like Parquet, ORC, CSV, TSV, JSON, or whatnot. You're also able to register files that are not necessarily local to your machine. They can be located on S3, they can be located on GCP. You can read those files directly from a remote location. This is taking a little bit longer, so I am going to do a kernel, restart kernel again. Let's try that. So the question I see in the chat window is that, will this be available on demand at all? If by all demand you mean that you can watch the recording afterwards, yes, we are currently recording the session and it's going to be available on our YouTube channel, which will, once it's posted, once it's published on YouTube, we'll go and tweet about. Okay, this is...
It's possible, Tom, that you got a new server.
Possibly,
and
yes.
It never imported any of the CUDA packages.
Maybe.
So
that might be.
It'll take a little bit.
Yeah. Okay. I'm gonna wait a little bit out. And then in the meantime, let's talk a little bit more about the Blazing context.
Perfect.
So the Blazing context is, as I say, that it's an entry point for everything that happens and that deals with Blazing SQL. So Blazing SQL and Blazing context is an entry point. You can create tables using Blazing SQL. Tables, just like we said, Blazing SQL is an engine. It's not a database. So the table here is quote, a table. It's effectively abstraction over a file. And that file can be pretty much anything. I see that it's finished importing, so I am going to start the Blazing context right now. In this particular example, we are starting Blazing context with with defaults, right? Everything is default. But there's multiple arguments you can actually pass to the Blazing SQL context, like the allocator. The allocator allows you to specify what kind of memory you're going to be using. So if you specify allocator equals to managed, like over here, oops, sorry about that. Then you get access to the so-called unified virtual memory, and that allows you to, should you run out of the memory on the GPU, Blazing context will seamlessly then move the necessary data to the host memory, and that happens seamlessly behind the scenes. So you don't have to worry that, oh, okay, my data set is 20 gigabytes, but I only have 16 gigabytes GPU. Blazing SQL will handle that, and then the transfer from the GPU memory to host, and it will only bring the data back if and when necessary to run the query. We mentioned before that you can scale this up to multiple nodes with multiple GPUs, and we use Dask to do that. The next argument you can pass on is the Dask client. So if you create a client all on top of the running Dask cluster, you can pass that client to the Blazing context as a parameter, and at that point, all the queries that you run using Blazing SQL will get distributed to run across all the workers that you have the access to. There's a bunch of other arguments, like the pool. You can actually create a pool. Pool, if you set it to true, will greatly improve the performance. We're not going to use it today, but it will greatly improve performance by pre-allocating a chunk of memory that is always used for RAPIDS or Blazing SQL, and it will effectively manage that memory allocation and deallocation behind the scenes in a much more performant way than you would do that with CUDA free and CUDA alloc. So that's that. You can try that should you have access to a GPU on your local machine. Okay, my Blazing context is ready. So we have now established Blazing context. Let's start doing some, playing a little bit with that. So first, we're going to start with data reading and querying. Our data, as I mentioned before, sits on S3. So this is a data from the Air Transportation Bureau of Air Transportation, I believe. I'm going to post a link later, later to the data set itself. But we are going to analyze, just very, very quickly, a timeliness of flights. In this particular case, we are going to look at the first 5 months of 2020, because that was when COVID hit, all the flights get canceled. So maybe we can check if the on-time performance of flights got better because of that. This data sits in our Blazing SQL BSQL bucket in the data folder, and this is a publicly available bucket. So whenever you want to use this data, you only have to do, connect it via S3FS, pass the anon equals to true, and then that way S3 is not going to ask you for any authentication credentials. You can read the data directly. In this particular case, we are just globbing everything, appending the S3 to the front of it. So all our data, we have 5 months, January, February, March, up to May, that we're going to read. So with QDF, the way we read data that is partitioned, in this case, we have the data partitioned by month. We effectively loop through all these files, read a parquet. So read parquet is the command that you're gonna use to read a parquet file. The storage options, just like we had before, we said that we don't require the authentication to connect to S3. But as you can see, I don't necessarily pass anything that is even slow, remotely related to S3FS, right? So this automatically, as soon as you pass S3 and colon whack whack, QDF or Blazing SQL will recognize that this data sits remotely on an S3 bucket, and then underneath the hood will automatically handle this, the read. So when we run this, what happens right now, we read this data in, you can see stuff is happening on the GPU. It took 5 seconds to read those 5 files. There was some movement of the data, and now we back in play. So let's have a look. What do we deal with? So the flights head brings five rows back to to host machine, so we can actually see what we have over there. There's a bunch of columns that, as you can see, are hidden. That's the normal way of presenting the data. Even pandas does that. But we have a bunch of columns up to, I believe, 54, and we're gonna look into them a little bit later on. But first things first, let's look how many flights we actually have in this data set. And that is as simple as saying, okay, well, just give me the length. If you're familiar with pandas, len is the way to check how long is your list. In this particular case, if you pass a QDF in this case, so if you can check what type is this. So we type flights. It's a QDF call data frame. If you pass QDF call data frame, this was already extended to actually give you the number of records you have in a data frame. In this particular case, we have 2.5 million flights that took off anywhere, took off between January 1st and May 31st, I believe. Same thing can be achieved with Blazing SQL. So we can read this data in a probably a little bit more flexible way. All we have to do is to pass and register the S3 bucket with the Blazing SQL context. So Blazing context, we register S3 bucket BSQL. And from then on, as soon as you execute this, right now Blazing SQL is aware of that. We have access to this this bucket on S3. And then when we pass the files, remember the files are defined as a list, we have effectively created a table that is called air transport. As you can see, not much has happened because we only effectively got, the Blazing SQL got aware that we have a data there. That's the table is sitting somewhere over there. We haven't done anything yet at the moment. But as soon as you run this query here, which is select star from this particular table and give me 5. So limit 5 is just like our head 5. You get pretty much the same result as we got before. So we have all the data, the first 5 rows that we have in that particular data. Now, to count how many how many flights we have in the data set, I believe this is simpler to do it that way. And you could have just literally do that as select star from that table and then pass it to len. But if you wanted to do it in a purely SQL way, you can just do select count star from the air transport, extract the count column, and take the first element from that returned CUDF. So yes, again, we have exactly the same the count. Okay. So as I said, we have a bunch of columns available to us in this particular data set. So the flights.columns gives you the full list as an index object, full list of all the columns that are available in this particular data set. We have a year, quarter, month, day of the week, flight date, unique marketing carrier, and then flight number, unique operating carrier. I'm not going to go too much into detail, what we have available in this particular data set. We're going to have a deeper down, webinar coming out this Thursday when we're going to analyze this particular data set in a little bit more detail. Today, we just literally just giving you a brief introduction to CUDF and then and Blazing SQL. Now, if you are more, if you'd like to get a bit of familiarity with what data types you have in any data set, and in this particular data set, we have, I believe, 54 columns. And then if you run flights.dtypes, you will get a list. It's actually I believe, a CUDF or CUDF series that gives you a list of all the columns with the associated data type. So year is integer 64, quarter is integer 64. Obviously, in this particular case, we don't need integer 64 to hold a year or quarter or month or day of the month, but that's the default that it, CUDF defaults for an integer types. We could have just literally go away with, int probably 16 or even in 8. Flight date, marketing unique carrier, as you can see, they are designed as objects. And we are going to actually operate a little bit on the objects today as well. In this particular case, the flight date is actually a date time. It's a daytime time. For those of you who are not familiar, or not aware, RAPIDS supports operations not only on integers or not only on floats or any numeric type. It also supports operations on datetime objects, dates, and also strings. So we're going to play a little bit with dates and strings later on today. And then you can actually exactly achieve the same thing by using Blazing SQL. So if we one more time run the top 5. Give me top 5 from the air transport table, you can see that Blazing SQL actually returns a CUDF data frame. And then at that point in time, you have access to exactly the same functionality that you have in a CUDF. I forgot to mention that if you guys have any questions, I'm not looking away. I'm just keeping an eye on the chat here. So if you have any questions or you want me to explain something else, just ask your question in the chat, and I'll try to get to it as soon as I can. Airlines and airports data. This came from the open flights data set. And it contains a list of all the airports and all the airlines that are pretty much worldwide, registered with different authorities. Airports D type. So this is the slightly different way of reading the data. In this particular case, we are using on ordered dict to create a list of names and associate that with the with the actual data type. So airport ID is the first column in the airport's CSV. And we need to do this because if you actually look, I'm not sure if I can do that here, but if you actually were to print out the first 2 or 3 lines from either of these files, you will see that there's no header. So we actually need to specify that header ourselves. Airport ID is the first column, and it's an int64. Name is a string, as I mentioned before, and we don't have any date types, date time data type here. So this is pretty much all we need to specify. But the difference comes when we read the data in. So read CSV, you can literally ignore these 2 things and then read the data directly in from the airport's path. But at that point, you would not have a header or the proper data type. So we are going to actually help the read CSV, the reader, that okay, well, my names, my columns, here's the list of names from this dictionary, and then here's the list of types, data types that you should be used for these columns. Once again, the storage options allows you to read from S3FS without any credentials when you pass the anon equal to true. So let's run that. That should be instantaneous because this is a tiny data set. So you can see we have the airport ID, name of the airport, city, country, IATA and ICAO. These are the international designators for different airports. IATA is mostly used by airlines. ICAO is mostly used by pilots. We have the lats and longs of those different airports, altitude, and so on and so forth. And same deal we're going to do with the airlines. So airlines, we have the airline ID, name, alias, and so on and so forth. So let's read that back in. So we have the airline ID, and then name of the airline, alias if it's available, IATA code if it's available, ICAO if it's available, and so on and so forth. So as Rodrigo showed you in the deck, we can create a table directly from a QDF. So in this particular case, we already read the data from airports and then from airlines. So we just created the table on top of that. And let's see what we can get out of this. So what we try to do in this particular case, we are going to extract the flight dates, the carrier name. So this particular information will come from the data set we aliased as B, which is airlines. So we're going to get the carrier name from there. What was the origin airport? So we're going to extract the origin airport's name and city from the airports table. And also we're going to link the destination. So that also is going to come from the airports table. So when you run this, you can see that there's something happening on the GPU, and there you have it. You have the right now we literally joined everything, so 2.5 million records in the air transport table, and right now we can get the carrier, the name of the carrier, where it flew from, the name of the airport and the city, and then where it was heading to. Same thing, as I mentioned before, you could literally do, so you don't have to read the data in using QDF. You could literally pass pretty much the same thing, so airport's path, the names and the D types to the create table column, call, and instead of reading the data directly into GPU memory, you only use that data when you, at this particular point in time, when you are calling the SQL using the SQL engine. So you can see we get exactly the same thing without really needing to read the data exclusively using QDF. And the same thing as we have, so the same query that that we have expressed in SQL, the same operation can be achieved using cuDF. And in my case, in my opinion, this on the other hand is much easier for me to read than doing all of these operations here that do pretty much exactly the same thing. Merge is an equivalent of the join. In this particular case, it defaults to a left outer join. There are different types. You can specify a parameter how equals to left outer, inner join, and so on. So we pass the left on is the op unique carrier, which is effectively this operator here, and right on is the IATA. So that's what we join in. We rename the columns. So this is the aliasing here. So B name as carrier name effectively gets operated here. And then the dropped column, because we don't need to carry over the IATA. So in this particular case, we get exactly the same data. It's the columns are shifted, but the data is exactly the same thing as we would get from the SQL query. OK. So there's a couple of questions we can ask, against this particular data set. So first things first, OK, well, let's check how many unique airports we have in this particular data set. For this, we are going to use flight origin, the unique call. So flight origin retrieves a single column, which in the RAPIDS nomenclature is a cuDF series. And then cuDF series has the unique call that we can extract all the unique airports in the data set. And then once again, we're going to use len to extract how many records we have in that particular data set. So we have 371 distinct airports. Same thing can be achieved with SQL. So select count distinct origin as count from the air transport. We extract the count and the first element from that particular data cuDF series at this point. And we have exactly the same results. Now, this is a data set that is super extensive, but how about we just do a basic analysis? So let's see how many flights were delayed and how many of them departed early. To achieve that, just like in cuDF, we can create a cuDF series that is either false or true. And maybe I'll copy that. I'll show you what I mean. So we can just literally do this, and it'll tell us which which record is greater than 0 in terms of the depth delay or less than 0. So this gives us a truth table that we can then pass as an, just keep these, these records that are true, keep them in my final data set. And then in this particular case, when we specify that the delay was greater than 0, it tells us that the flight was delayed by that many minutes. In this particular case, if it's less than or equal to 0, it tells us that the flight was actually departed on time or slightly earlier than it was scheduled to fly. So when you run this, it tells us that in this particular data set, remember we had 2.5 million records. We have 500,000 flights that were delayed, and roughly 1.75 flights that left on time or early. So let's see how does this distribute, right? So only telling us that, okay, there's 500,000 flights that were delayed. Okay, what does it tell me? So we can create these interim tables here, delays and on time, which effectively is reusing all of this, right? And then we only extract the depth delay column, and we're going to bin it into 100 different, distinct bins, right? And then in this particular case, we are going to, let's create this, create some bins and use those bins. So the bins is effectively a monotonically increasing list of cutoff points. So these are the delimiters of different bins as in a histogram. And we are going to use a digitize method from cuDF series that accepts the list of bins to create a bin representation of that of our delay times, and then we're going to group by those particular column, and then count how many occurrences we have in this particular data set in this particular bin, and divide that by just created the, okay, out of 500,000, 60% of them were delayed by that much. And that's what actually happens here. So we are going to set a new index. We want to see not necessarily just the index 0, 1, 2, 3, but the actual delayed minutes. And then we're going to move it to pandas. So this is the exact call that you would use if you want to move the data from GPU to host. And then once, and that gives you back a pandas data frame that you can then use to plot. We're going to plot a bar chart with this figure size. The limits on the y-axis are going to be this, and the title is going to be this. So let's run that. This shouldn't take too long. And then, as you can see, most of the time, most of the delays were anywhere between 0 to 15 minutes, right? So roughly half of the delayed, delayed flights were anywhere between 0 and 15 minutes. And then the next one, roughly 18% of all of those were delayed between 15 and 30 minutes. And 30 and 45 minutes was another, I believe that would be around 7%. So as easy as this, you can literally very quickly analyze and summarize the data, 500,000 records. In literally 3 seconds, you have already an answer to the question, okay, what is the distribution of these delays? Do I need to be worried? If I saw most of my delays somewhere between 120 minutes and 135 minutes, I would be worried because most of my flights, lots of my flights would have been delayed by 2 hours, and that's definitely not acceptable for any airline manager. And then same thing, we can actually analyze, okay, let's look at the on-time distribution, right? So how many flights, what is the distribution of flights that actually departed early or on time? So most of the flights actually departed on time, right? So there's, not most, but plenty of time that depart on time or slightly earlier. And then that early time is, they normally, rarely go past beyond 15 minutes, departing 15 minutes too early. Some of them depart, quite a few of them actually depart around 5-minute mark, so between 5 and 6 minutes early than planned. But quite a few of them, it's actually a normal, what you would expect from seeing from the distributions of delays. And then next one, what are the top 10 airlines and airports with most delays? So let's have a look at the data set from a slightly different way. We're going to look at the delays and on-time performance for all the 10 airlines, top 10 airlines and airports with at least 1,000 flights. So let's recreate our tables, delays and on-time. And what we're going to do, look at here is check by origin, right? Check by origin. So origin, airport, and the city and country. How many flights were delayed? And what was the average delay time for those flights that actually delayed from that particular origin airport? Having count greater than 1,000 tells us that because we are grouping by origin, name, city, and country, we want to, just like we posed the question, we want to see the origin airports with all at least 1,000 flights. We are going to order the returned table by the average delay and in the descending order. So we want to see the most delayed because that's what we said. And we're going to return top 10. So if you run this, you can see that the Norfolk Airport had 1,300 delayed flights, and the average delay was around 1 hour. So you can see that these flights, either there was plenty of outliers, or actually on average they delayed around 57 minutes. Savannah is another one, a big hitter, Charleston, Washington Dulles, and so on and so forth. And we can do the same analysis for destinations. So what are the destinations that are most frequently delayed, and by how much? Well, O'Hare is the most delayed. So those 21,000 flights that were on average delayed by 55 minutes that were heading to Chicago, and Newark was another one, and Dulles again. And same, let's look at the carriers. So which carriers are the most frequently delayed and by how much? Commute Air, that's one of the carriers, 3,800 flights. almost more than an hour on average. Air Wisconsin, more than an hour on average. Trans-States, GoJet, Gandalf, and so on and so forth. So as you can see, it takes literally no time to ask these questions against any data set. And that's the beauty of the, both Rapids and Blazing SQL. You can ask almost any questions against even large data sets, as I'm going to show you later, in literally seconds. And something that used to take us, minutes running in using pandas. And what are the most? Let's look at the most punctual ones. So the most punctual ones is Dallas Love Field. So roughly, 1,500, flights that departed either on time or 3 minutes early. Houston, another one. William P. Hobby. So mostly Texas is represented here. Chicago Midway is another one that is normally scheduled to depart on time. And same thing, we can see, okay, where are they going? So once again, we have, Houston, we have Chicago, we have Dallas that are most, on time, most most of the flights are on time, and with the shortest, as close to the departure time as they advertise. So that's a good thing for the carrier, that we are on time, we're not delayed, we are not leaving early, which is a good thing. And then same for the carriers. Who's the most on time? Southwest Airlines, the average delay is roughly 4 minutes. Delta Airlines, 4.5 minutes. Earlier. Spirit Airlines, Horizon, American Airlines. So the big names are here, and they mostly, at least when they arrive on time, they are mostly departing on time. And as I mentioned before, Rapids can operate on dates and strings. So in this particular case, we are going to check how many flights per month and day of the week we have. So as you can see, we extract the year, month, day, and day of the week from the flight date. We could have done that because we already have this information in the data itself, but I was trying to showcase that all you have to do is to pass the .dt and then extract the year, month, and so on and so forth directly from the date-time file. So here's the distribution of how many flights departed on January, February, March, April, and June, and so and May. And then same thing, let's have a look at the distribution of flights throughout the week. So there's a dip. This is the normal average time, flights per weekday. 5 is Saturday, so we see less flights on Saturday. And then this is a very, very big proxy for finding the international airports. But what we try to do here is to look, okay, let's take a regex and find the word international in the name of the airport, and that way we can check. Okay, in our data set we have 898 international airports with the word international in our data set. I'm not going to go through this. If you want, you can just follow the instructions here and create your API key for Google Maps and paste it here. And this way you can plot the points on the map using Google Maps to to find out where those international airports are. I'm going to switch gears now and then show you how you can run a similar, pretty much the same code, but on a much bigger data set, and also on a in a distributed form. So there's a couple of small differences when we start using Dask, but most of the code is pretty much the same. The main difference, while this is starting, the main difference between running things using cuDF on a single machine with a single GPU versus running stuff on Dask is the fact that Dask is implements a so-called lazy execution paradigm. What that means is that until you ask Dask to actually compute something, to do the work, Dask is not going to do anything. It will delay the execution until you tell it to actually run this workflow. What happens in the meantime, as you add new calls to to your execution. You say, okay, well, just take this data and then select only these columns, and group by this, and sort values by that. What happens is Dask is actually creating an execution graph. Graph that when you tell it to either persist or compute, it will only then start executing that data. So I am going to actually, I think, open this one. Which one? Yes, this one. OK. I need to update the IP of this. So just bear with me for a second there. This is the Dask cluster. I'm going to use this to connect. So this part here is connecting to a Dask cluster. So when you create a private cluster, just like I already have here, right? So I have multiple private clusters, private GPU clusters. You can create a cluster anywhere with a GPU, dedicated GPU between 1 and 64 GPUs, and it's dedicated for you. You can run it there. When you do that, we automatically start a Dask cluster for you, so you can connect the client to that running Dask cluster. I'm going to start running this, and okay. I think I need to paste this. OK, so now we can check what is happening as the data executes on the Dask cluster. I'm going to just pull out that and then progress. Come on, hop, and stack it like that. I kind of like looking at this way. So right now, as you can see, we have a Blazing context that is using a Dask server behind the scenes. So whatever gets returned right now from from running the SQL query, it's going to be a Dask QDF, i.e., it's a data frame that hasn't been executed. It's just literally a list of tasks that until we call .compute is not going to execute. And then in this particular case, we are going to use the data from 2018 January to October 2020. And as I said before, we can use pretty much the same code as we had before. Dask QDF is the only change. So we use Dask QDF. Instead of using QDF, we use Dask QDF to read all of these files. We can run flights head, which you can actually see right now. What's happening behind the scenes is, I'm going to make this smaller. What happens behind the scenes is that Dask right now is pulling out the data from AWS, and it's going to return our the row of 5 QDF of 5 records here. Come on. And then we can literally reuse the same, the same calls as we had before. So length of flights, it will give us exactly the same results as before. There must be some delay on the S3 because that shouldn't take that long. I am going to give it another kick and restart this. Whoops. There we go. Let's restart that. Let's try that again. Okay. Load it up. And create the context. So you can see we are right now initializing the context behind the scenes. So every worker gets the Blazing context effectively initialized. And the head node is going to communicate with all the workers to do the work. Should be up and running in a second. And then we're going to read those files again. Come on. Seems like AWS doesn't like me this morning. There we go. Okay, so we have that. We read the files, and now there we go. So we have, pretty much the same code. When you run this, you can actually see that the task is executing a bunch of, tasks underneath the hood. So len chunk, you could see that in this particular case, we have 20 million flights that departed between 2018 and 2020 October. Same thing can be achieved with Blazing SQL, right? So we can create a table directly from the top of the files. You can see that how we created that. And then the only difference when we call the Blazing SQL, because it returns a task QDF, we need to call the .compute in order to get those results back. And same thing here. So you can see that we got 20 million records again. As before, Dask QDF has access to Dask columns and Dask D types. Columns and D types, and same thing with Blazing SQL. So we can just extract 5 records from the data and run with it. Same deal with the airlines and airports. This way, actually, we are reading and creating the using QDF. So you can literally, join both Dask QDF and QDF data frames together and work with them simultaneously. You don't have to, everything doesn't have to be a Dask QDF when you operate with QDF. One thing that I think I didn't mention is that .persist instead of .compute. The difference is that the .persist loads the data into memory and then it's still distributed on all of the workers, whereas .compute runs the query on all the workers and then returns the results back to the head node. So that needs to be used when it's really warranted and then with caution. Once again, it's very simple. You can see that it takes 3 seconds. Previously, it was taking 1 second. It takes 3 seconds on 4 workers to execute this query, and then same deal happens when we do that with Dask QDF. How many unique airports we have? It should be roughly the same, 391. So probably some of the airports that there were some flights to the airports that were dropped because of COVID during 2020. How many flights were delayed or departed early? You can start seeing that how this whole thing gets executed by Dask and Blazing SQL or Dask QDF behind the scenes. This is a very useful useful chart that helps you to actually pick and see what's happening behind the scenes. 6 million flights were delayed, 13 million were left on the same time. Same deal with pretty much the same code, with the distinction that the Dask QDF series doesn't have the digitize, digitize call. So what we do, we actually wrap that and run this particular, method in each partition by using map partitions and passing the bins to it. So we can do this, and we are going to get yet again a plot of how many flights, what is the distribution of flights that were delayed. It hasn't changed much, but always with a larger data set, larger data, you can actually in this particular case, we don't get much, much a different picture, but there are circumstances where this is useful, and it takes only 8 seconds, right? So you don't have to wait. You don't have like 20 million rows, 8 seconds on 4 GPUs. That's gonna be fast. Same deal with the delays. So the most, I'm going to just, we are almost on time, so I'm going to just skip through these. I am not sure what happened here. I think we run out of memory. So I'm going to pause here because we are 3 minutes away, and I'm going to give you guys some time to, ask questions. I'm going to just scroll through here. The only thing that I added to the rest of the calls is the .compute. So I'm actually instructing Dask to run this for me. But you can see, and you can compare that with the other one, the other code. The calls are the same. So I didn't change pretty much anything here. This is exactly the same calls as we had before. to extract the year, month, day, and day of the week as we did in QDF. .compute only gets added here, and then we sort index because the data is distributed. When it gets collected on the head node, the index is not in line, so we just sort the index, and we off to do something else. So I'm going to pause here. Rodrigo, if you want to add anything, by all means, please jump in. And guys, if you have any questions, I would be happy to try to answer them. Thank you.
No, thank you, Tom. That was awesome. As always, I always love seeing how easy it is to get started with a very little bit of data and then scale it up with multi-GPU using Blazing notebooks and Dask and all these things kind of together the way that we're using them. So thanks a lot for walking us through that. If anyone has any questions, this is a good moment to ask them, but otherwise, just to fill you in, we're going to be running 2 of these webinars every other week. So there's another webinar scheduled for Thursday, where we're going to go over some more workloads. And as the year progresses, a lot of these webinars are going to be focusing on different aspects of the RAPIDS ecosystem. So we work on Blazing SQL ourselves, but there's a lot of other components that are really interesting and cool in terms of what the packages allow you to do when performance really isn't an issue anymore. So please check that out. You can always follow us on Twitter. That's where we have all of the latest and greatest information about what's going on in Blazing SQL and the RAPIDS ecosystem. Any announcement, anything that's going on in any way, shape, or form will always hit Twitter first. You can also please subscribe to our YouTube channel. The entire live stream is hosted on our YouTube channel, or all of our webinars are hosted on our YouTube channel, so you can check it out there. And we really appreciate, everyone who came to check this video out. And thank you very much, Tom, for putting all this together and showing the world what you can do with Blazing SQL and the RAPIDS ecosystem.
Anytime, and I hope to see you guys on Thursday.
All right. Thanks a lot.
Thank you.
Everyone have a good one.